So welcome to the Picture Language Seminar. We're very happy today to have Dietmar Bisch. Dietmar is a big expert on subfactor theory. He was at UCLA and later professor at UCSB and now at Vanderbilt. But Dietmar is not only famous for his work in subfactor theory, but he made Vanderbilt into one of the leading mathematics departments in the United States. And today he's going to tell us about the wondrous world of hyperfinite subfactors. Dietmar.
Okay, well, thank you for the very nice introduction, Arthur. So let me share the screen. Okay, can everybody see it?
Yes.
All right, great. First of all, it's a pleasure to be at Harvard, even though it's just virtually. It's always nice to be at Harvard, right? No matter in what capacity. Today I want to talk to you a little bit about hyperfinite subfactors, which is an extremely rich world that has created a lot of really interesting and new mathematics. Since this audience here is very varied, lots of people who obviously are not experts in subfactors, I will take some time to kind of introduce the concepts so that at least you will understand or get some idea of the kind of stuff that we are thinking about. Okay, so let's start with talking about what the words in the title mean, hyperfinite subfactors. What do I mean by a subfactor? Well, a subfactor will be simply an inclusion of so-called 2-1 factors. And what are these 2-1 factors? Well, the 2-1 factors are von Neumann algebras. So they are algebras of bounded linear operators on a Hilbert space that are closed under taking adjoints, that contain the identity, and that are also closed in a certain weak topology, namely the topology of pointwise convergence on vectors, also called the strong operator topology. Such an algebra of operator is called a von Neumann algebra, was introduced by von Neumann back in the 40s. This algebra is called a factor if it has trivial center. So if the center of the algebra is just the scalar multiples of the identity operator. And well, in this case, of course, the algebras are highly non-commutative, right? There's nothing that commutes with everybody else except scalar multiples of the identity operator. And when is such a factor of type 2-1? This is a classification that Marian von Neumann introduced. Well, it's of type 2-1 when it's infinite dimensional and when it has a trace, which is just a linear functionals on M that has the trace property. So in other words, trace of xy is equal to trace of yx. And it's of course positive. So the trace of a positive operator is a positive number. Okay, that's called the tracial state. We want it to be normalized. So the trace of the identity is 1. Okay. Such algebras actually exist, and let me talk to you about one of them today, the so-called hyperfinite 2-1 factor. So when is a 2-1 factor called hyperfinite? Well, it's called hyperfinite if there is a sequence, an increasing sequence of finite dimensional star algebras, such that you can write your 2-1 factor M as the weak closure, so the closure in this topology that I described earlier of the increasing union of the ANs, right? So that's called a hyperfinite von Neumann algebra. So how would you construct one? Well, let's take the ANs to be the 2 to the n cross 2 to the n matrices and embed them into the 2 to the n plus 1 cross 2 to the n plus 1 matrices diagonally twice, right? You take a matrix and you embed it into the next bigger algebra twice diagonally. Then you go ahead and take the union of all of these algebras. You take the closure in the operator norm, if you like, then you get a C-star algebra. And this C-star algebra has, of course, a trace, which is just the extension of the normalized matrix trace to the closure of the algebra. Those of you who work in operator algebra, you know that this is called the UHF algebra of type 2 infinity. It's the uniformly hyperfinite von Neumann algebra of type 2 infinity, which also appears in physics, the so-called CAR algebra. Well, so how do we construct from this the hyperfinite 2-1 factor? Well, whenever you have a C-star algebra and a state on it, then you can build a Hilbert space from it. by simply defining the inner product of two operators using the state. So in this case, the inner product of an operator x and y would be defined to be the trace of y star x. And then you look at the corresponding Hilbert norm, which is just the square root of the trace of x star x, i.e. the inner product of x with itself, right? Then you complete the algebra in this in the norm induced by this inner product, and you get a Hilbert space. And of course, the algebra acts on it simply by left multiplication, right? A, in this case, would be dense in the Hilbert space. So left multiplication is a densely defined operator, and you show it extends by continuity to the whole Hilbert space, and you get a representation of the algebra on this Hilbert space H. And then what you do is you take the closure in the weak topology, so the topology of pointwise convergence on vectors of this algebra, and you get a von Neumann algebra, and this von Neumann algebra is called the hyperfinite 2-1 vector, right? So it's simply a union of the 2 to the n cross 2 to the n matrices, and you take the closure in this weak topology, okay? So a few facts about this guy. First of all, it is easy to see that the trace actually extends to the reclosure, okay? So R has a trace as stated above. You can show as an exercise that it is highly non-commutative, so it has trivial center. And then it's not very hard to see that if you compute the traces of all the projections in this hyperfinite 2-1 vector, then you end up with a full interval from 0 to 1. This is, of course, a very interesting feature, right? Because you know that if you take the matrix trace of a projection in the n by n matrices, well, what is it? If it's not normalized, it's just the dimension of the space onto which the projection projects, right? So you can therefore think of this trace to be a notion of continuous dimension that naturally comes with every 2-1 vector, in particular the hyperfinite 2-1 vector. Now you may wonder, you know, why do I call this the hyperfinite 2-1 vector? Because obviously, instead of taking the 2 to the n cross 2 to the n matrices to construct such an algebra, I could have taken the 3 to the n cross 3 to the n matrices and embedded, you know, everything 3 times instead of just twice, but do otherwise the same construction, and you know, you get the same algebra. Well, at the C-star level, when you take the norm closure, you actually get something that's not isomorphic, but it turns out that as soon as you take this weak operator closure, you actually do get something that is isomorphic, and this is a result that Murray and von Neumann proved back in the 40s. They showed that there is actually a unique hyperfinite 2-1 vector, right? And not only is it unique, it's actually the smallest one, because it's a very simple exercise to show that if you have any 2-1 vector, then you can always embed the hyperfinite 2-1 vector into it. So in that sense, it's the smallest 2-1 vector that there is. It's of course infinite dimensional, right? Any questions about this? Okay, I guess not. Then let's go on. So this explains the word hyperfinite subfactors, right? So by hyperfinite subfactors, I simply mean an inclusion of 2-1 vectors that are both hyperfinite, right? And so Kohn in 1976 proved that if you take a subfactor of the hyperfinite 2-1 vector that's infinite dimensional, then it's actually isomorphic to itself, okay? And so in another result that he proved in this context was that if you take an amenable ICC group, so ICC means that all non-trivial conjugacy classes have infinite cardinality, well, then the corresponding group for Neumann algebra, which is just the algebra that you get by looking at the left regular representation of the group on little L2 of G, is actually another copy of the hyperfinite 2-1. So there are many ways, in other words, to describe this hyperfinite 2-1 vector. You can think of it as group algebras. You can think of it as just an increasing union of finite dimensional algebras. And you know, all of these constructions give you this very nice algebra, the hyperfinite 2-1 vector. However, as this result of Kohn shows, that if you look at subfactors and you look at them as individual algebras, well, you don't learn anything about the hyperfinite 2-1 vector because everybody is isomorphic to the big algebra itself, right? So you need to do something cleverer than just looking at the isomorphism type of the subfactors if you want to find out something about R. And so this is what this is where Warren Jones comes in. He proposed in 1983 that what we should be looking at is the position of n in R. So in other words, we should look at the pair n in R up to isomorphism. And what do I mean by that? Well, I mean that if you take another subfactor Q in R, then this subfactor here would be isomorphic to the first one. If there's an isomorphism from R to R, that carries n into Q, right? So whenever we talk to subfactors, then we mean up to this notion of isomorphism, so up to isomorphism of the pair, okay? And so then, of course, the first question is, okay, we want to study the position of the subfactor in R. What kind of invariants do we have? And, you know, whenever you have mathematical objects, it's natural to look at their representation theory. And we have a representation that we have already constructed here, namely the Hilbert space H that I use to construct R, right? So you can think of H as being just the completion of R in the Hilbert norm induced by the inner product. And this is usually denoted as L2 of R because it's a non-commutative L2 space, okay? And well, it turns out that this Hilbert space is not just a left R module or left N module, right? So N and R don't just act by left multiplication on this guy over here, but it's actually an NR bimodule because N acts by left multiplication and R acts by right multiplication on L2 of R, simply in this, you know, very trivial way, right? So L2 of R is very naturally an NR bimodule. And well, this is called the standard representation of the subfactor, okay? So the Hilbert space that I constructed earlier carries a natural left N action by the subfactor, and the right R action by the factor, and hence is an NR bimodule, okay? Now this guy is called irreducible if it's irreducible as an NR bimodule, and that amounts to saying that the commutant of n in R is trivial. What does this notation here mean? It just means all the operators in R which commute with all the operators in N, right? And this consists then just of the scalar multiples of the identity. So irreducibility of the representation is the same as saying that the commutant of n in R is trivial. It's just scalar multiples of the identity operator. And in this case, we call the subfactor irreducible, okay? And obviously, you know, in order to say something about subfactors, we can restrict ourselves to irreducible subfactors because you always can decompose a representation into irreducible pieces. So we are really interested in understanding irreducible subfactors of the hyperfinite 2-1 factor, okay? All right, so the very first thing that one looks at is something that goes back to Murray and van Neumann. Namely, they showed that whenever you have a representation of any 2-1 factor on a separable Hilbert space, then it's actually classified by a number, the so-called coupling constant. And let me just explain what that coupling constant is briefly. Namely, one can show that our Hilbert space L2 of R decomposes into a certain number of copies of L2 of n, let's say k of them, and a little piece, and the little piece is of the form L2 of n times p, where p is a projection in n. Now this guy over here is of course a left n module, right? Because n just acts by left multiplication on these L2 of n's. And one can show that any Hilbert space can always be decomposed in that way. And hence there is a number attached to it, which just measures the n size of the Hilbert space, right? And that number is the number of copies of L2 of n, plus the size of this piece over here. And that piece has size trace of p. So it only depends on the trace of the projection, which is easy to see. And so this number is called the Jones index. You know, L2 of R carries k copies of L2 of n and trace of p copies of L2 of n. And you get a number here, which is bigger or equal than 1, right? Because n is a subfactor of R, so there is at least one copy of L2 of n in there. And this number could be a priori any positive real number bigger or equal than 1, because as I mentioned earlier, the trace of p can take on any number between 0 and 1, right? We have this notion of continuous dimension. And indeed, if you look at all the left n modules, then of course, each one of these guys here is 1. And so any number bigger or equal than 1 does appear as a coupling constant. However, Jones showed that if you look at these particular Hilbert spaces, which arise as the representation Hilbert spaces from a subfactor, then not every number bigger or equal than 1 appears. And in fact, the index is what's called quantized. So if the number is between 1 and 4, then it has to be of the form 4 cosquared pi over n. And then above 4, any number can appear. This is the famous Jones rigidity theorem that he proved in 1983, right? So this was a big surprise, and Masamichi, for instance, was one of the first people who learned about it, and he was also blown away by the result. I mean, it's absolutely surprising for anybody who worked in von Neumann algebras at the time. So from now on, we will assume that the subfactor n in R is not too small. So in other words, the index of n in R is always finite. Okay.
Dietmar, can I ask a question? This is
sure.
So for the decomposition for L2R as a left n module, so there are also Hilbert spaces.
Right.
Is there a canonical inner product decomposition?
So that you can write down an explicit a map that goes from L2 of R into L2 of n. So I'm not quite sure what you mean by canonical. The only thing that matters is really how many copies of L2 of n you have and what the trace of P is. So it's completely canonical in that sense.
Well, what I mean is that, when you direct sum to Hilbert space, you have many different ways to choose the inner product, right? You can.
Oh, by this I just mean the orthogonal direct sum.
Oh, okay.
Right.
Okay.
Yeah, sorry for that.
Okay.
It's just the orthogonal direct sum of Hilbert spaces.
Okay. Okay. Thanks.
Any other questions about this? Okay. All right. So now let's go back to the representations. So as I mentioned earlier, we are looking at L2 of R as the standard representation. And whenever you have a representation of a compact group or whatever you like, then of course there is another representation that comes with it, and that's the contra gradient representation on the conjugate Hilbert space. And in this case, the contra gradient of the NR bimodule L2 of R will be an Rn bimodule, and the Rn bimodule rho bar is just L2 of R, but now as an Rn bimodule. Okay, so you have these two natural representations that come with every subfactor. And then what you do is you proceed a la Hermann-Weyl, you tensor them together, and you decompose into irreducibles. So for instance, you take L2 of R, which is an R bimodule, and L2 of R as bar as an Rn bimodule. You can take the bimodule tensor product over R, then you can take tensor powers of this guy over n now, and you get all of these guys will be NN bimodules, and then you can decompose them into irreducibles, and you get a whole bunch of irreducible NN bimodules, right? And well, you can play the same game when you do rho bar tensor rho. Now you have to tensor over n, and over here over R, you decompose, you get a whole bunch of irreducible RR bimodules. And when you multiply each of these guys one more time with either rho bar or with rho, then you end up by doing the same procedure with NR and Rn bimodules, right? So just from the standard representation and its contra gradient, you are producing a whole bunch of new representations, which are all NN, RR, NR, or Rn bimodules, right? And well, this gives rise to what's called a standard invariant of the subfactor. Namely, you just look at the intertwiner algebras, the algebras of intertwiners, of these particular representations. So for instance, you look at rho tensor rho bar to the L, and you look at the NN intertwiners, that's an algebra. And you can of course do the same thing for NR, RR, and the Rn intertwiners. And the nice thing is that they sit in each other in sort of an obvious way, right? If you take an N intertwiner of rho tensor rho bar to the L, and you tensor that intertwiner with the identity from the right, well, then you get an NR intertwiner of the Hilbert space rho tensor rho bar to the tensor L tensor rho, right? And similarly, you have inclusions from below by taking an intertwiner over here and tensoring it with the identity from the left. And these guys sit in each other again by tensoring an intertwiner from over here with the identity from the right? So all these algebras of intertwiners sit in each other in this particular way. And obviously, you know, this is not a structure which is trivial, right? It's a rather complicated structure, if you like. But it's a fact due to Vaughan-Jones that it can actually be computed by performing the so-called basic construction of the subfactor. And, you know, this is something I will get to a little bit later. What I want to mention at this point is that this standard invariant here, this guy, turns out to be an amazingly rich mathematical object. Soren Popa axiomatized it back in the mid-90s as a so-called Lambda Lattice. Vaughan-Jones reformulated it as a planar algebra, and he showed that it has a very rich combinatorial structure with, you know, planar tangles acting on it and so on. And one can then use topological arguments to manipulate operators on Hilbert space, right? All of these intertwiner spaces are algebras of operators on Hilbert space. Which Hilbert space? Well, these Hilbert spaces over here. And this planar algebra structure allows us to manipulate these operators topologically using topological arguments, right? So this is sort of the power of Vaughan's planar algebra picture. And then if you're a category person, then you might want to look at these guys as rigid C-star tensor categories, which you can also do. And there is another equivalent reformulation of this object as rigid C-star tensor categories with, you know, distinguished Frobenius algebra objects in them and so on. And you should notice that there is a natural set2 grading of this structure, right? Because we have Nn and Nr bimodules. And then, of course, there is in the category picture a Morita equivalence between them, which is actually given by L2 of R as an Nr bimodule. But anyway, I don't want to get into this. Just to let me mention that this object here is really extremely interesting, extremely rich, and a lot of amazing mathematics has come out of trying to classify and understand these objects. For instance, you know, new fusion categories have been found, new modular tensor categories came out of it, and so on.
So, Dietmar, can I ask a question here too?
Sure.
So a priori, let's talk about the case which I'm familiar with. Suppose we get this rigid C-star tensor category or something. So a priori, this is an infinite amount of data, right? The L goes all the way. But if you get a category, it definitely should be a finite amount of data, right? It would be just some pentagons. So do those squares stabilize in the end, or they are encoded by some finite amount of data?
So they will stabilize precisely when the subfactor is finite depth, right? And that's the fusion category case. So in general, they will not. But you know, in special cases it might, and that's the finite depth case.
Okay, I see. Okay, so it's fine. Thanks.
But in general, you know, indeed, you will have a rigid C-star tensor category with infinitely many simple objects. Okay, and then, you know, it doesn't stabilize. Right?
I see. Thanks.
So I'll come to some examples in a minute.
Yeah, I have a quick question. Can you elaborate on the lambda lattices in the previous slide?
Sorry, yes.
The lambda lattices, what are those objects?
The lambda lattices is an axiomatization of Soren Popa of inclusions of finite dimensional algebras that arise as standard invariants of subfactors. Okay. And he called it the lambda lattice. It's just the double sequence of inclusions of finite dimensional algebras. So this is what I was going to say on the next slide. So what is this object G and R? Well, it consists of a double sequence of inclusions of multi-matrix algebras. So these guys and these guys are sequences of inclusions of multi-matrix algebras that are included in each other as indicated here. But there is one additional property of these guys, and that is that the upper left corner and the lower right corner, they are actually orthogonal modulo the lower left corner with respect to a natural trace that always is on the biggest algebra. And that natural trace actually comes from the subfactor. So I'll come back to this structure in a minute. This is called the commuting square structure. Okay. It's a very interesting combinatorial structure that naturally arises whenever you have a subfactor. But let me, before I can explain that, I need to explain a couple of other things. So the first thing that I need to explain is the notion of a fusion graph or a standard graph that kind of captures the algebraic information that is contained in the standard invariant of a subfactor. So the standard invariant consists of intertwiner spaces of NN, NR, RR, and Rn bimodules, right? And the question is how is the fusion of these bimodules described? And it turns out that we can extract some graphs from this by in the following way. So we have two graphs, bipartite graphs, where the vertices are given by irreducible NN and irreducible NR bimodule, respectively RR and Rn bimodules. And the graph, the edges are given by the fusion of taking an irreducible RR bimodule and tensoring it with a standard representation from the right. So for instance, in this example, if you take this guy A, you tensor it with a standard representation from the right, well, then you end up, right, so this is an NN bimodule, this is an NR bimodule, so this is an NR bimodule, and the graph tells you how it decomposes into irreducible NR bimodules. In this example, it would be just B plus C, right? So it turns out that that structure actually describes completely this inclusion over here, okay? So that's a so-called fusion graph. And there are two of them, right? Because you can play the same game with RR and Rn bimodule by taking a guy over here and then tensoring it from the right with the Contra gradient representation, okay? And there's maybe one more thing that should be said, namely the odd vertices, so the vertices at this level here, they are in bijection, right? Because you get from an Rn to an NR bimodule simply by taking the Contra gradient. So the Contra gradient map gives an identification of the odd vertices of the two graphs, gamma, gamma, prime. Okay? And that is a combinatorial structure that is used when one tries to figure out what graphs actually can appear. In general, this pair of graphs will be a bipartite, connected, possibly infinite pair of graphs. And it comes with more information. It also comes with a particular eigenvector, which we call the standard eigenvector. And that eigenvector, those of you who know what I'm talking about, basically just captures the quantum dimension of these objects. If you want to think of them as objects in a category, or in subfactor language, the standard eigenvector captures the indices of the corresponding irreducible subfactors of the hyperfinite 2-1 vector that is represented by these bimodules. Okay. Now, if the graphs gamma and gamma prime are finite, then these are just Perron-Frobenius eigenvectors of gamma gamma transpose or gamma transpose gamma appropriately normalized. So Perron-Frobenius theory comes in very naturally here. Okay, so I want to give you an example, and I'm going to kind of focus on the infinite depth case because that's the case that is not so well understood. And one example that appears in nature is where both of these fusion graphs are the Coxeter-Dinkin graph of type A infinity. And in that case, the standard invariant of the subfactor is what we call trivial or minimal. It consists of the Temperley-Leib-Jones algebras. And those of you who know what the Temperley-Leib-Jones algebras are, then you know that they depend on a parameter. And the parameter in this case is just the square root of the index, okay? Now, the Temperley-Leib-Jones algebras are always subalgebras of these intertwiner algebras. So they're always there whenever you have a subfactor. And in case the standard invariant is just them, well, we call it minimal, or sometimes I will also just say trivial. Of course, it's far from being trivial, right? Those of you who know Won's work, I mean, you know that he used the Temperley-Leib algebras and the representations and the trace that comes from the subfactor or the 2-1 vector in which they live to construct his not invariant, the Jones polynomial. And so, you know, there is some amazing mathematics there, even in this case where the standard invariant is minimal or trivial, okay? But to come back to trying to understand subfactors of the hyperfinite 2-1 vector, the very first question is, well, how good of an invariant is the standard invariant, right? And this was kind of the main topic of research back in the 1990s. And Sorin Popa developed a beautiful theory of amenability of the subfactor. There are many sort of equivalent ways of looking at this in terms of hypertraces, in terms of a weighted Föllner type condition, which is absolutely beautiful for the subfactor and so on. But then at the end of the day, he found another description, which is very easy to describe, namely that of amenability of a graph. And what he defined the graph to be amenable if the norm of the graph is equal to the index, right? So gamma is the graph that comes from the subfactor. It's one of these diffusion graphs. And it turns out that these guys are bounded linear operators on little L2 of the vertices. And as a bounded linear operator on little L2 of the vertices, they have a norm, right? And the norm of both of these principal graphs are equal. They are always the same. For instance, in the case of A infinity, you can do it as an exercise. The norm squared would be 4. And the subfactor, the graph rather, will be called amenable precisely when the norm is equal to the index, okay? So in general, the norm is less or equal to the index. We always have this inequality. And when it's equal, well, then we call the graph amenable. And the beautiful theorem that Popa proved, which is extremely hard and deep in 1994, is that if you have a subfactor of the hyperfinite to one factor with amenable graph, well, then the standard invariant is a complete invariant. So for instance, this happens when we have finite depths. So when these graphs here are finite, and by the way, the graph gamma is finite if and only if the graph gamma prime is finite. So what that means is that in this decomposition of the tensor powers of the standard representation and its contra gradient, you have only finitely many non-equivalent irreducibles that appear. Well, in that case, indeed, the subfactor is completely classified by the standard invariant and can in fact be reconstructed from it. Okay. So this theorem kind of closed the story for so-called amenable subfactors of the hyperfinite to 1. And what I want to point out is that if you take a subfactor of the hyperfinite to 1 factor whose index is bigger than 4, that has just trivial or minimal standard invariant, well then by this theorem, it must be non-amenable, right? Because the graph norm is 4, but the index is bigger than 4, so it's not amenable, okay? And so in that case, you know, we have no idea whether the subfactor is classified by the standard invariant or not, and most likely it is not. And that's kind of the topic of my talk, okay? Any questions about this? Okay. Right, so now a lot of work was done on trying to classify the standard invariants of subfactors, and I don't want to get too much into this because that's a separate talk all by itself. But you know, trying to understand what graphs.
Yes. Hi, can I ask one question?
Sure.
So about that graph gamma and gamma prime, when can we say that gamma and gamma prime are same? In general, they need not be same. So if they are same, can you say something about the subfactor?
I don't know any result in that direction, no. Okay. So I guess one thing you can say is that if they are not the same, then you know n into m and m into m1 will not be isomorphic. So you know one necessary condition would be n into m and m into m1 are isomorphic, but even in that case, you know, the graphs are not necessarily the same. You know? I mean, if they are,
in the two cases, it will be same.
Yeah, right. So if n into m and m into m1 are the same, then the graphs are the same. But it could be that the graphs are the same and n into m and m into m1 are still not isomorphic. That happens for, I think, E6 or E8. Okay.
Thank you.
So it's complicated. Okay.
Thanks. Thanks.
Okay. Right. So to come back to what I was just talking about, so one of the things that you can do now is try to figure out, you know, what are all the possible graphs that appear, what are all the possible standard invariants that appear, and a lot of work by a lot of people has gone into this for index less or equal than 4, which is the area, you know, where the index is quantized. This was done back in the, I guess, 80s and 90s. It's the ADE classification of the subfactor. So this is kind of the old story. And basically from 2000 to 2014, something like 10, 15 years of effort of a lot of people went into trying to figure out what all the standard invariants up to index 5 plus 5.25 could be. And a whole bunch of new subfactors were found. For instance, the famous Hagerup subfactor or the extended Hagerup subfactor by Bigelow, Peters, Morrison, and Snyder. And Grossman, Tanner, Pennies, and many others have contributed to this, and of course Jones as well. So I don't want to get into this. This is an amazing story. But the point that I want to make here is that we can. What has been shown is that there are countably many finite depth subfactors, so countably many standard invariants where the graphs are finite, and those subfactors are all automatically hyperfinite. And all the other standard invariants in this index range, so up to 5.25, have infinite graphs, and those are either A infinity or in index 4, D infinity, and they could also be A minus infinity, infinity in the reducible case, but let's just concentrate on irreducible case. So in other words, we only have A infinity, so trivial temporally, and one non-trivial one at index 4, okay? And what Jones and I proved is that, in fact, the first non-trivial infinite depth subfactor that you get appears at index 3 plus square root of 5. Now, 3 plus square root of 5 is 5.236 and so on, so slightly below 5.25, right? And it turns out that, in fact, the classification between 3 plus square root of 5 and 5.25 is highly non-trivial. There's a lot of hard work that goes into this. And that was done by Morrison, Pennies, and Asfali, if I remember correctly. However, the theorem that Vaughan and I proved was that there are non-amenable irreducible subfactors with index 3 plus square root of 5 and infinite fusion graphs, and the fusion graphs are these particular guys. Okay, so this one and this guy. Okay, so these are tree-like graphs, and those of you who know what I'm talking about, these are actually special cases of the so-called Fuchs-Catalan subfactors that Vaughan and I discovered. Now, it follows from a result of Sore and Popa, and by the way, the construction method for these subfactors is quite a sophisticated construction. It's a so-called free product of standard invariants that Vaughan and I invented. But the nice thing about this free product construction is that it follows from a result of Sore and Popa's, that whenever you have a standard invariant that comes from a hyperfinite subfactor and another one coming from a hyperfinite subfactor, then you can always arrange them freely in such a way that they again exist for a hyperfinite subfactor. So by this result of Soren's, it follows that these guys actually do exist in hyperfinite world. Okay, there are hyperfinite subfactors with these infinite graphs, and they are non-amenable, because the norm of these two graphs is less than 3 plus square root of 5, okay? So the standard invariant will a priori not classify them, at least we don't know whether it does or not, right?
So what are the even and odd vertices?
So the even is here, right? And then you just count 2. So even, odd, even.
Oh, so just count.
Odd, even,
okay.
it's just draw it as a bipartite graph.
Okay.
The first vertex here is always even, right? So this corresponds, to L2 of n, and this corresponds to L2 of r, the first vertex, right?
Okay, thanks.
All right. Any other questions about this?
Yeah, actually, what's the norm again? You said it's not 3 plus square 5. Is known the norm of them?
I think it's in the paper that Vaughan and I have.
Okay.
So I have a
It's not the easy number. It's not 4.
No.
Okay.
Okay. All right, so I want to maybe briefly describe a few open problems in this context, because now we have moved to this world of non-amenable hyperfinite subfactors, and there are many obvious questions in this context. The first one is, of course, which standard invariant or which planar algebras actually do arise from hyperfinite subfactors. So, for instance, do all the Temperley-Leib-Jones standard invariants for every parameter delta bigger than 4 arise as hyperfinite subfactors? The conjecture is that that is not the case. then, of course, a subproblem of this is what are the indices of irreducible subfactors of the hyperfinite one vector? That's a problem that goes back to Vaughan Jones that he posed in his original article in 1983. And you know, I made this point earlier that a subfactor of the hyperfinite one vector whose index is bigger than 4 with trivial standard invariant, so with just Temperley-Leib-Jones standard invariant, is non-amenable. And so the obvious question is, well, is there another subfactor of the hyperfinite one vector with the same standard invariant, so in particular the same index, that is not isomorphic to the first one, right? So are there always at least 2? And the answer, the conjecture would be that this may very well be the case, because there is a classical result due to Ogneanu and Jones about actions of amenable groups of the hyperfinite one vector that suggests that something like this might be true. Namely, Ogneanu showed that if you have an amenable group with an outer action on the hyperfinite 1, then up to outer conjugacy, it is unique. That corresponds to the fact that the amenable subfactors of the hyperfinite 1 are classified by their standard invariant. And then Jones showed that as soon as you take a non-amenable group, well, then you can always construct at least 2 actions that are not outer actions on the hyperfinite 1. So that would correspond to this question over here. Given a non-amenable subfactor, you can construct another one with the same standard invariant that's not isomorphic to it, okay? And then, of course, you can ask a concrete question, namely, you can look back at these subfactors that Vaughan and I constructed here, these hyperfinite subfactors that are non-amenable. And those are the first non-trivial ones, right, with index above 4. And you can ask, well, is there another one, you know, with the same standard invariant that's not isomorphic to the one we constructed? And in fact, you know, are there many such, right? And it could very well be that there are many. Now, when Soren Popa gave a talk in the seminar, Zheng Wei was asking the question, well, so what do we do in non-amenable world? You know, what invariants do we have? Well, that's exactly the problem, right? We need to look for invariants that go beyond the standard invariant. And more importantly, we need more examples to even get some idea, right, of what, where we should be looking. So we need to construct infinite depth hyperfinite subfactors, and we need to look for invariants beyond GNR. And one of these invariants I want to talk about, and it's inspired by this work of Jones on actions of amenable groups on the hyperfinite 1. Now, before I come to that, let me give you a couple of constructions of the hyperfinite 1 vector that are sort of the most basic ones. And again, I'm always interested in just irreducible hyperfinite subfactors, right? Now, there is sort of the world of group actions and group representations and quantum groups at roots of unity and, you know, C-star tensor categories and so on that allows you to construct subfactors of the hyperfinite 1. And most of these constructions typically lead to finite depth subfactors, okay? Well, there are some exceptions, like you can use group representations, for instance, to get infinite depth amenable subfactors as well. Now, a very simple construction is a construction that was suggested to Uffe and myself by Vaughan. And these are subfactors of this type here. I will just call them group type inclusions. Vaughan at some point baptized them the Bisch group subfactors. So that's that word has stuck with it, I guess. And so how are these guys constructed? Well, it's very easy. You just take 2 finite groups H and K. You let them act outerly on the hyperfinite 1, and any group, by the way, any locally compact second countable group has an outer action on the hyperfinite 1, so sits in the outer automorphism group of the hyperfinite 1 vector. It's a huge group. And then you simply take the fixed point algebra under the H action sitting in the cross product under the K action. And I should point out that both of these guys are hyperfinite, right? This one obviously because it's a subfactor of the hyperfinite 1 vector, and this one is just a finite extension of a hyperfinite, and hence it's also hyperfinite, okay? So this way you get hyperfinite subfactors, and then you can use group theory to analyze the structure of these guys. So for instance, if you take a group that's generated by the 2 finite groups, that is generated by 2 finite groups H and K. So in other words, G is some kind of a quotient of the free product of H and K, right? Which, by the way, is already interesting if you take Z2 and Z3, right? Because the free product of Z2 and Z3 is PSL2Z. So quotients of PSL2Z would, for instance, fit into this context. Well, then you can very easily show that you get irreducible subfactors precisely when the groups have trivial intersections in the outer automorphism group, which is automorphisms modulo inner automorphisms. And by inner automorphisms, I just mean automorphisms of the form ad u, where u is a unitary. We show that it's infinite depths precisely when this group is infinite. And now these two results are really easy. And the one that takes a little bit more work is this one here. We show that it's amenable in the sense of Popa. So in other words, the fusion graph of this subfactor is equal to the index, which in this case is just the product of the cardinalities of the two finite groups. Well, that happens precisely when the group is amenable, okay? So amenability of the subfactor translates for these examples in amenability of the group that's generated by H and K. And then, of course, you can, construct many examples, right? And I'll come back to this class of examples in a minute. Another more what I call bare hands construction of subfactors is the one using commuting squares. So commuting squares is a structure that appears very naturally in subfactors, and this lambda lattice that I described earlier consists of a double sequence of such commuting squares. Okay. Now, what is a commuting square? Well, let me just explain it in the context of multi-matrix algebras. So the algebras AI and BI that you see here are all direct sums of matrix algebras. They could be infinite direct sums of matrix algebras, but we always assume that we have a normal faithful trace that is given on the biggest one. So in case this guy is an infinite direct sum of matrix algebras, this would be an L1 weight vector, right? That would give you such a normal faithful trace, okay? Now, when is this guy a commuting square? Well, this guy is a commuting square when these two algebras here are orthogonal modulo the small one. So I wrote this over here in the algebra B1, which you view as a Hilbert space with the inner product that comes from the trace, right? As before, the inner product is of two operators is the trace of y star x, okay? So when you have this kind of orthogonality condition, you have two subspaces that are orthogonal modulo the small one. This can be, by the way, rewritten in terms of conditional expectations for those of you who know what I'm talking about. Then the structure is called a commuting square. And by commuting square, I simply mean, the conditional expectations commute, right? This is so if you project this way, then that's the same as projecting that way. This is why we call it a commuting square. Okay, now it turns out that this structure is completely natural in the context of von Neumann algebra. Von Neumann algebras, whenever you have an inclusion of von Neumann algebras and you take commutants in this way, so you take the commutant of A and C and the commutant of A and D, you get this inclusion. Then you take the commutant of B and C and the commutant of B and D, you get that inclusion. They obviously sit in each other in this way. Well, then this is automatically a commuting square. So taking commutants, okay, which is an algebraic operation, gives rise to this amazing orthogonality structure of four algebras. And this, by the way, is something that has been used in quantum information theory by Reuter and Vickery in order to construct error correcting codes. So this structure definitely, I think, should be more relevant and more exploited in the context of quantum error correcting codes. Okay, so let me give you an example of such a commuting square, just to the simplest example that's out there, where the smallest algebras are just the complex numbers and the diagonal matrices. And of course, the complex numbers are embedded n times in the diagonal matrices using this graph. Then the diagonal matrices sit, so you think of the diagonal matrices as the algebra C plus C plus C, right, n times. That sits in the n by n matrices by giving that graph. And the inclusions on the other two sides are given by the same graphs, right? Then what you do is you move the diagonal matrices by a unitary a little bit away from it, right? So you look at the algebra U delta U star, and then you ask, well, with respect to the inner product given by the trace, when is this guy a commuting square, okay? And this is an exercise you can do in your lunch break. It turns out to be a commuting square precisely when the unitary matrix is a complex Automar matrix, i.e. when the absolute values of all of the entries of your unitary are 1 over square root of n, okay? So, so you can see that already in this very easy example, you get some very nice thing, right? You get complex Automar matrices. And these, of course, exist for every n, right? Just you just take the Fourier transform of the cyclic group Zn, right? So, e to the 2 pi I rs divided by n or something like that. And you have an example for every n. Now, it turns out that if you are interested in complex Automar matrices, then there are actually many more. For instance, for n equals 7, you can show that there's a one-parameter family of complex Automar matrices that all give such commuting squares, and they are all non-equivalent in a certain sense. Okay? So there's possibly one-parameter families out there. All right, so this just gives you an example, and this type of structure Wurm calls a spin model because the UIJs are spins in a statistical mechanical model. Okay. All right, so then when you have such a commuting square, you can construct a subfactor from it by doing what? Well, so here is your commuting square that you start with. The graphs that give you the inclusion of the multi-matrix algebras are denoted by G, H, K, and L. And then you need a certain non-degeneracy condition, which I denoted over here of that commuting square, so certain compatibility conditions of the inclusions. And more importantly, you need a particular trace on the biggest algebra, and this trace is a so-called Markov trace. It's, for instance, given by a parent Frobenius eigenvector of LL transpose or of GG transpose. But let me not get too much into this. But if you have such a structure, well, then you can construct hyperfinite subfactors from it by iterating the so-called basic constructions. So what you do is you look at the orthogonal projection from B1 onto B0. This is a Hilbert space, right? Because it has a trace. You define the inner product as before. You call that projection E1. And then you look at the algebra that B1 and E1 generate, and you call it B2. And under this non-degeneracy condition over here, the orthogonal projection that you get from A1 to A0 will be E1 restricted to A1, and you get, when you look at the algebra that is generated by A1 and that orthogonal projection, an algebra A2. And then the fact is that this guy over here is again a commuting square. Okay, it again has this orthogonality condition, and you can iterate the construction. And then at the end, you take the union of the algebras and you do, as before, this representation of the union of these algebras on the Hilbert space that is defined by the trace. You take the V closure of the union and you get a hyperfinite phenomenon algebra, which, if the trace is extremal, which it will be, for instance, if all these inclusion graphs are finite and connected, and the Markov trace comes from parent Frobenius eigenvector because of uniqueness of the parent Frobenius eigenvector, you will get hyperfinite subfactors, which under very mild assumptions on the graphs will be irreducible. Okay, so what this gives you then is hyperfinite subfactors whose index are the norms of these graphs. Okay, so this is a bare hand construction of hyperfinite subfactors. Okay, so let me not get too much into this, but obviously, this bare hand construction leads only to hyperfinite 2-1 factors whose indices are certain numbers. If you are the norm of a finite graph, then you have to be an algebraic integer. And by the way, the smallest one that has been constructed is 4.026. It's the norm of the graph E10 squared. This goes back to Ogneanu and Hagrup's Skau back in 1990. And when I was a postdoc in Berkeley, Wurm asked me whether I know of an irreducible subfactor of the hyperfinite 2-1 factor whose index is a rational number, i.e. not an algebraic integer, right? Because if you are rational and algebraic integer, you have to be an integer. And I didn't know, so I got to work and I actually constructed one whose index is 4.5. And it's based on an infinite commuting square, obviously, right? Because finite commuting squares only give you algebraic integers of this type, where the inclusion graph is this guy over here. And I have a student who has constructed a few more examples with rational index recently. Now, by the classification, this subfactor of the hyperfinite 2-1 factor has trivial standard invariant, just Campbell-Leib standard invariant, and you know, we don't know much about it. Okay, so the question is, what do we do? So now I come to this notion of non-commutativity. So can I have 5 more minutes, Arthur?
Yes, sure.
Okay. So, so I need to find now an invariant that allows me to distinguish subfactors, you know, that goes beyond beyond the standard invariant, because the standard invariant is trivial, right? And so, inspired by the work of Vaughan on actions of non-amenable group of the hyperfinite 2-1 factor, one place to look is at central sequences. Okay, and central sequences, if you like, are a certain notion of non-commutativity of the subfactor relative of the big factor relative to the subfactor, right? Obviously, all subfactors are highly non-commutative because they are factors, but there is still a notion of asymptotic commutativity of one algebra over the other. And so what do I mean by that? Well, so I define a relative notion of property gamma, which, by the way, I've done back in my thesis. And so what I say is that the subfactor n into m has property gamma if there are non-trivial central sequences for the big factor contained in the subfactor. Okay, so what does this mean? It means that you get a bounded sequence with values in the subfactor n that asymptotically commutes in the 2 norm with every operator in M, and it is non-trivial. So non-trivial just means you don't become more and more a scalar, right, as n goes to infinity. So xn stays away from scalars. Now, this is a notion of asymptotic ergodicity, which has been studied in ergodic theory as well. And it turns out that the right way to study this is actually in the phenomenon algebra context, if you look at the so-called central sequence algebra that's associated to it. And the central sequence algebra is a very familiar construction for phenomenon algebras, but perhaps not so much for physicists. So what you do is you look at the C-star algebra of infinite sequences with values in a 2-1 factor m, and then you mod out by a certain two-sided ideal, which is a norm-closed two-sided ideal, which is obtained using a free ultrafilter on n. Now, those of you who don't know what a free ultrafilter is, you can simply think about it as a point in the Stone-Jack compactification of the natural numbers minus the natural numbers. And so if you have a bounded sequence, right, then, you know, the limit of such a bounded sequence always exists, right? It's just a limit point in the Stone-Jack compactification. And so if you look at all those sequences whose 2 norm as n goes to omega is 0, then that forms a two-sided ideal in the C-star algebra. And if you mod out by it, then you get a C-star algebra. Now, why in the world are we taking a complicated free ultrafilter? Well, the reason to do that is that if you take a free ultrafilter, then you actually end up with a phenomenon algebra. And it's not just any phenomenon algebra, it's a trivial phenomenon algebra. If you didn't do the ultrafilter thing, but just take the limit as n goes to infinity over here, that you can still do, you just get a C-star algebra, you don't get a phenomenon algebra, right? Okay, and so what we do then is we study this notion of central sequences of M that are contained in N, which is called property gamma. And so this property gamma then transforms into a property of this algebra, namely the central sequence algebra M prime intersection in omega has to be non-trivial. That's the same as saying that the subfactor has property gamma. So there are central sequences that asymptotically commute with M contained in the subfactor N. Now there is a stronger notion that's called Mcduff, and that notion is that if you take the subfactor N into M, then it has to be isomorphic to N into M tensor R, so it splits a common copy of the hyperfinite 2-1. And the theorem that I proved back in my thesis, which is a relative Mcduff type theorem, which is the proof is exactly the same as Mcduff's original proof, is that N into M has this property, is Mcduff, precisely when the relative central sequence algebra is non-abelian. And in fact, you can then show that it is automatically a 2-1 phenomenon algebra. So as soon as it's non-abelian, it's big, okay? And so now it's clear what to do, right? How to distinguish subfactors. Namely, you just look at properties of this central sequence algebra. Well, it could be trivial. It could be abelian, in which case it's automatically diffuse, or it could be non-abelian, in which case it's automatically very big, right? And so, I like to think about these 4 properties or 3 properties as properties of non-commutativity of the subfactor. And the more central sequences you have in the subfactor that are central for the ambient 2-1 factor, well, the more commutative the algebra becomes, right? Okay, so this is a degree of non-commutativity for the subfactor. And so what about examples? Well, all the examples that we described earlier, so the finite depth subfactors or the amenable subfactors, well, they are very abelian because M prime intersection and omega is a 2-1 factor or 2-1 for Neumann algebra, right? Now, the subfactors that we construct from commuting squares, well, those bare-hand constructions also give very commutative examples because the Jones projections and the Jones projections by 1, which do not commute, as you all know, they give non-trivial central sequences in the subfactor that are central asymptotically for the ambient factor. So they are all very commutative examples, right? So all those hyperfinite subfactors that we normally construct and consider, they are all very commutative in this sense. Okay. Now, what about non-commutative examples? Well, it turns out that we can construct non-commutative examples, and simply by doing this construction that I alluded to earlier. Okay, so the theorem that I proved a year ago is the following: if you do this group type construction of subfactors, you take a group that is generated by 2 finite group. Well, then you can show that the corresponding group type inclusion has property gamma. So it has this non-trivial central sequence algebra precisely when the infinite index inclusion that you get by looking simply at the cross product of the group on the hyperfinite 2-1 factor has property gamma. And you can show the same result also for Mcduff. Okay. Now, this result now is then very easy to use to construct non-commutative hyperfinite subfactors, right? And all I need to do is I need to look at an action of a group G on the hyperfinite 2-1 factor such that this inclusion does not have property gamma, and I get a subfactor that does not have property gamma of finite index as well. And in fact, in order to do that, it's enough to just look at an action of G on R such that the corresponding subfactor does not have property gamma, right? Because inclusion property gamma is stronger than ambient factor property gamma. Okay, and so that's what we do. As I said here, all you need to do is look at this action. And in fact, it turns out that there are lots of examples because any strongly ergodic action of a non-inamenable group on the hyperfinite 2-1 gives a cross product that does not have property gamma. And so, for instance, if you take a property T group, for property T groups, ergodic actions are automatically strongly ergodic. Well, you can find property T groups which are quotients of PSL2 sets. So they are quotients of the free product of Z2 and Z3. For instance, that's the case for SLNZ for all n bigger or equal than, I think, 29. I've forgotten the exact number here, some larger number, just because, for smaller n's, you have certain finite quotients of SLNZ that would not be 2-3 generated. But anyway, if you take such a property T group, you take the Bernoulli shift action on the hyperfinite 2-1, well, then the corresponding cross product does not have property gamma. That particular example actually goes back to Joda. And hence you get an index 6 subfactor that has no central sequences in the subfactor for the ambient factor, so is very non-commutative, right? And this one is automatically irreducible because Z2 and Z3 do not have a non-trivial intersection, right? Just because of 2 and 3. And so this gives an irreducible subfactor of the hyperfinite 2-1 factor with no central sequences, and hence it is very non-commutative. And in particular, what that means, and I think this is sort of the big surprise of this story, is that there are subfactors of the hyperfinite 2-1 that cannot be constructed from commuting squares, right, in the way I described below. So there is no way you can find some kind of commuting square that will approximate a subfactor, because that would result in a very commutative subfactor. Okay, I stop here.
Thank you very much, Dietmar. Your beautiful picture looks like Alice in Wonderland's garden, and you've taken us on a really nice tour. We have to come and visit you in Vanderbilt so you can do it in person.
That's right.
So let's open up the floor for discussion. When you ask questions, it would be good if you could turn on your video so we can see you and talk to you.
Yeah, I just wanted to ask a question about about a year ago,
Can you turn on your video, Stan?
Oh yeah, just a second. Yeah, so about a year ago, Quant's embedding conjecture was disproved. And I wonder what does that, if it has any implications on the theory of subfactors.
Well, so I mean, I'm talking here about subfactors of the hyperfinite two-unfactor, and of course, you know, the hyperfinite two-unfactor can be embedded into R omega, right? So, you know, it might eventually have some consequences on the theory of subfactors, but you know, the two-unfactor that cannot be embedded into R omega must be a very weird two-unfactor, right? Nobody has been able to actually write down a particular example. And of course, you know, once we have a particular example, then we could look what kind of subfactors that particular example has, and you know, we could see whether there are some consequences on the world of subfactors on that particular two-unfactor that is not embeddable into R omega. But you know, I rather doubt that it has any implications on subfactors of the hyperfinite two-unfactor, since everything is embeddable there.
So does your technique, you know, have any? Do you have any suggestions on how to approach this problem of constructing this particular factor? That this...
if I had, then I would be working on it and not talking to you guys. No, I don't think anybody has an idea. And you know, I think one problem is that not too many people really understand the proof by Wittig and co. That work in operator algebras. You know, so what we really need is some operator algebraists who can somehow make the necessary translations of the work of Wittig et al. In order to understand that proof, right? So at this point, I think nobody has any clue of how to construct such a two-unfactor. But you know, some ideas have been floating around which would involve very different techniques. You know, from what I've been talking about. You know, more like maybe random matrix techniques or things like that. You know, there's probably maybe there's some probabilistic way of constructing these two-unfactors, you know.
Okay, thanks.
But I mean, I doubt that these techniques will be very useful.
I have a question about the central sequences. You're looking at sequences in the subalgebra that are approximately central in the big algebra. What about the other way around? Looking at, of course, there are lots of central sequences in the big algebra. Right. But what about sequences that are only supposed to commute with elements in the subalgebra? I wonder, does that have any interest?
You can also do that, and people have certainly done that, right? You look at, instead of looking at m prime intersection m omega, you look at n prime intersection m omega, right? And so that is always a huge algebra, as you said. It's always a 2-1 for Neumann algebra. But certainly, you know, you could look at things like, okay, you know, what about m prime intersection m omega contained in n prime intersection m omega? You know, what kind of a subalgebra is that? And yeah, this has been studied, and you know, people have looked, for instance, in the finite depth case at this particular, in the finite depth case, n prime intersection m omega is again a 2-1 factor. and that contains, let's say we talk about hyperfinite, right? M prime intersection M omega, which then would also be a 2-1 factor. So you have actually constructed a new inclusion of 2-1 factors, which you can study, and you can look at their standard invariant and so on. And this has been done, you know, way back when. There might even be something in the book by David Evans and Yasukawa Higashi about it. You know, this goes back to Ogniano, in fact.
Well, thank you.
Yeah, but you know, so this here is really the correct notion for what I want to do here, because I want to somehow say something about the non-commutativity of the big factor over the subfactor, right? Some kind of asymptotic non-commutativity. And the curious fact is that the commuting square constructions, you know, always gives you very commutative things, but in general, you may have very non-commutative things as well, and hence they cannot be constructed using commuting squares. You know, and that is a surprise, at least it was to me.
So I see several people are unmuted. Chengwei, did you want to?
Yeah.
Or you're talking.
Can I ask a totally stupid question?
There are no stupid questions, Jörg.
So when you look at relativistic quantum theory, it is full of subfactors, but it is always mostly type 3-1.
Right.
What of your theory extends to that situation?
So quite a bit, if you like. I mean, in terms of quantum symmetry, so standard invariance, the standard invariance you get from type 3-1 factors are the same standard invariance as the ones that you get from type 2-1 factors. So there's nothing new if you are interested in trying to you know, look at what kind of quantum symmetries you have when you move to the bigger world of type 3-1 factors. And in fact, you know, there is a result that Sorin Popa proved a long time ago, I guess, which is that if you take a finite depth type 3-1 hyperfinite subfactor, then it's always of the form hyperfinite 2-1 factor tensor, you know, the hyperfinite type 3-1 factor. So, but I guess the answer is that in terms of standard invariance, you know, you don't find anything new when you allow type 3-1. Okay, was a very good question, Jörg.
Thanks for the answer.
Hi, Dietmar, I have a question.
Hey, Xingwei.
This is Zheng Wei. First, it's a very beautiful talk, and you translate the group composition of group subfactors to group actions, and then you can compute the properties like property gamma and the central sequence. Well, if the subfactors are not group-like, then you get non-trivial compositions of non-group-like subfactors.
Right.
Like this actual index 3 plus square root of 5.
Right.
And then is there any chance to compute the central sequence for that?
Well, you know, that's why we do research, right? So I think for that particular case, you know, where you do a free composition of two standard invariants that live in hyperfinite world, it's a way of arranging those two fusion algebras, let's just call it that way for a minute, in the world of bimodules of the hyperfinite 2-1, right? And so there might be different ways, you know, of arranging things in there, which might be a different way of proving that there are, you know, many non-isomorphic examples with the same standard invariant by arranging them in such a way that they are not conjugate or whatever, you know. Now, in terms of central sequence algebras, you know, that will not be so easy to compute unless you have a specific realization of the 2-1 factor, right? You know, one point that I did not make, and let me maybe use this opportunity to make this point, is what was the idea, you know, that I had by when I started to investigate this matters? Well, the idea was that I wanted to construct subfactors that have no relative central sequences, right? So where the central sequence algebra is trivial. And then I can very easily construct another subfactor that has the same standard invariant just by taking the original one and tensoring it with the hyperfinite to 1, right? When you tensor it with a hyperfinite to 1, then you don't change the standard invariant. That guy still has the same standard invariant, but it has now a big relative central sequence algebra by my theorem, right? So the theorem that I proved back in my thesis was that, you know, if you split the 2-1 factor with a hyperfinite to 1, well, then the central sequence algebra is big. It's a 2-1 phenomenon algebra. So the goal, in other words, would be to construct subfactors that have no relative central sequences, and then you always get another one, right? Just by tensoring the original one with a hyperfinite to 1. And it's not the standard invariant that will distinguish them, but it's the central sequence algebra. And that was precisely the idea that Bohn had when he constructed, you know, 2 actions of non-amenable groups on the hyperfinite to 1 factor that are not autoconjugate. And it's, you know, the distinction is made by looking at some ergodicity property at infinity. So by looking at central sequences for the action, and then, you know, once you have one that is ergodic at infinity, well, then you get another one just by tensoring it by the identity, which corresponds to precisely doing this, you know. So that was the idea. Now, of course, you know, the goal would be, well, how can we construct subfactors of the hyperfinite to 1 with A infinity standard invariant and no central sequences, right? And if we could do that, well, then we could prove the analog of Vaughan's theorem, you know, the converse to Ognian's theorem, by then just getting a second non-isomorphic A infinity hyperfinite irreducible to 1 factor by simply tensoring the original one with a hyperfinite to 1. But, you know, how to do that, as I said, you know, we need to come up with other methods of constructing hyperfinite subfactors. And, you know, maybe eventually we'll find some. I mean, like one place to look for would be, you know, to relax the notion of commuting square a little bit, right? You know, commuting squares, what?
Well, as you mentioned, for the commuting square construction, you would get the central sequence to be as large as a 2-1 factor.
Right, yeah.
If you want to get this trivial central sequence, then you need the highly non-commutative construction. Maybe infinite graph somehow with free product.
So, something like that, you know, and I mean, you know, unfortunately, also when you do infinite commuting squares with infinite graphs, as long as it fits into, you know, the usual framework with iterating the basic construction, well, you get the same result, right? You still get lots of central sequences. So somehow you need to do something, you know, add some randomness, as Sorin called it in his talk, you know, to kind of destroy the central sequences, you know. But, you know, if I knew how to do it, I would have done it already.
Thank you.
Okay.
So are there any other comments? There are lots of experts here.
And so let me make one additional comment here, you know, so the standard invariant is really just, you know, the representation theory of the subfactor, but, you know, this work with central sequences clearly shows, you know, that there is more to life than tensor categories, right? So in other words, you know, the subfactor captures other symmetries as well, not just symmetries coming from the representation theory that's then, you know, captured in an associated planar algebra or tensor category. And this commutativity property of the subfactor, or non-commutativity property, as I prefer to call it, you know, could be viewed as some kind of a quantum symmetry of the subfactor, you know. And I've talked about this in other contexts. You can think of this as being, you know, some kind of a correspondence or a map, you know, between hyperfinite factors that is more commutative or more non-commutative than others, right? So I think that you know, that could have some relevance in physics as well.
Well, thank you again, Dietmar, for a very beautiful presentation. And we'll look forward to your coming back with some new results and more results.
Sounds good. Well, thank you, Arthur, for inviting me.
And next week we have Anton Alexeyev, and see you then. Bye-bye. Bye-bye.
Okay, bye.